Welcome back, and let's take a second look at the structure of recursion trees. Remember that recursion trees represent the execution of a divide and conquer algorithm, and in particular the sequence of recursive calls. Now, the time complexity or runtime of a divide and conquer algorithm is characterized by the recurrence relation of this form. And since every node in a recursion tree corresponds to one execution of the body of the algorithm, either the base case if it's a leaf node, or the recursive case if it's a non-leaf node, the bottom line is that every node in the recursion tree corresponds to one execution of the algorithm. And therefore, the larger the number of nodes in a tree, the higher the runtime of the algorithm. So, since the runtime of the algorithm is governed by the values of A, B, and D, the next question we look at is how do the values of A, B, and D affect the structure, and in particular the size of the recursion tree, and therefore the runtime of the algorithm. So first we're going to look at the constant A. Let's take a simple example, or a small one, where A is equal to 2. We get a tree exactly like the previous one. But here what we're interested in is counting the total number of nodes in the tree as well as the total number of leaf nodes. So as before, we have a total number of leaf nodes equal to 8, and we have a total number of nodes in the tree equal to 15. And the important thing to realize here is not so much the actual values, but the fraction of nodes that you can find at the leaf level. Notice 8 is more than half of 15. In fact, it's 53%, which means more than half the nodes can be found at the leaf level. So what happens when A gets larger? Let's look at the case where A is equal to 3 and the depth of the tree, that is the number of levels in the tree, is the same as in this smaller example. So let's count the number of leaf nodes. We have a total of 27 leaf nodes and a total number of nodes in the whole tree equal to 40. So the first observation is that as A gets bigger, the total number of nodes gets bigger, and also the proportion of the nodes that are found at the leaf level also went up from 53% to 67%. Next, let's take a larger value of A. Say A is equal to 7 as in Strasson's algorithm. Now, I don't have enough room to draw the tree, but it's easy to compute the number of nodes in the leaf level, and that's equal to 343. It's basically 7 to the power 3. Now the total number of nodes in a tree is equal to 400. So clearly, as A gets bigger, the total number of nodes gets bigger. And again, the proportion of nodes that appear at the leaf level out of the total number of nodes in a tree is still bigger. In this case, it's 86%. So in conclusion, A does not affect the number of levels in a tree. However, it affects the width of each level. That is the number of nodes at each level. And the biggest level is the leaf level. So that's not surprising. Remember that the total number of nodes per level is equal to A to the power of the number of the level. So we have A power 0 nodes at this level, A power 1 node at this level, A power 2 nodes at this level, and A power 3 nodes, and so on and so forth. So of course the size of each level, or the width of each level, grows very fast. Basically we have an exponential explosion since we're multiplying by A the number of nodes every time we go down one level. So that concludes our discussion of the effect of A on the structure of the recursion tree. Now let's turn our attention to the second constant, B. Remember that B does not directly affect the structure of the recursion tree. However, it does so once we know the value of n. So let's say n, which is the input size at the root node, is equal to 64. And let's pick a constant value of A of 2, which is the smallest value that makes the tree interesting. So let's say we start with a value of b equal to 8. What is the shape of the tree? Well, every node is going to have two children except for the root node. And the question is, how many levels are we going to have? Well, remember that every time we go to the next level, the input size is cut down by a factor of 8. So starting at 64 at the root level, we're going to go down to an input size of 8 at the next level and an input size of 1 at the next level. So this tree is only going to have two levels under the root node. Now, how can we determine that without building the tree? Well, remember the number of levels is equal to the log base b of n. So in this case, we have the log base 8 of 64. So that means how many times do you divide 64 by 8 until you get 1? And the answer is 2. Notice that we started with a pretty large value of b. So let's see what the structure of the recursion tree looks like when we reduce b to 4. How many levels would this tree have, given that we use the same value of n and the same value of a? Well, we compute log base 4 of 64, and the answer is 3, which means this tree will have 3 levels under the root node. And here is the computation we just did. So, b went down, but the number of levels went up. Let's see if the trend continues for an even smaller value of b, say b is equal to 2. Well, the answer is yes. In fact, I don't have enough room here to draw all the levels, so let's just do the computation. The number of levels is equal to log base 2 of 64, and the answer is 6. So the conclusion is that the smaller b, the larger the number of levels. So in conclusion, the value of b determines the depth of the tree. That means the total number of levels under the root node. Now, that's not surprising, because remember, the number of levels in a tree is the number of times you can divide n by b until you reach 1. So the smaller the base of the logarithm, the more divisions it takes until you reach 1. And therefore, the larger the number of levels under the root node. So that is the effect of the value of b on the structure of the recursion tree for a given n and a given a. Finally, let's look at the last constant in the recurrence relation, that is d. Now, d does not directly affect the structure of the recursion tree so much as the interpretation of it. So let me remind you of the interpretation of the recursion tree. Each node in that tree corresponds to one execution of the body of the divide and conquer algorithm whose runtime we're studying. In particular, the leaf nodes correspond to the base case executions of the algorithm, where there's no recursive call, and the interior nodes in the tree correspond to the recursive case executions, when we do make recursive calls. And remember, the children of a node corresponds to the execution of the recursive calls. Now, the edges, on the other hand, represent the actual recursive calls. So, for example, this node corresponds to the execution of the original call to the recursive or divide and conquer algorithm. This edge corresponds to the first recursive call. This edge corresponds to the second recursive call. So the question is, where does the constant d come into the picture? Well, for that we have to think back about the runtime of the algorithm. First, we have the runtime of the base case execution. That's typically a constant. We can just call that c. So the work done at every leaf node is just the constant c. Now, how much work is done at this node? Well, without counting the execution time or the runtime of the recursive call, the only work done at this interior node is the time it takes to perform the divide step and the time it takes to perform the combine step. So in conclusion, and this is true for every node, of course, so what this means is that for every interior node here, the runtime of the algorithm that matters is just the function g of n. That's all the work you do besides the recursive call, because the runtime of the recursive call is taken care of by the children of the node. That's where you compute it. So the important thing here is that for the leaf nodes, the runtime of these nodes is just a constant, call it c, whereas for every interior node, the runtime at these nodes is just g of whatever the size of the input is for that level in the tree. So if the input at some node has size n, then the runtime at this node is just on the order of n to the power d. That's the function g of n that we are looking at specifically here. So in other words, for every one of these interior nodes, the runtime is n to the power d, because the input size is n here. Here we would have n over 8 to the power d. That's the runtime, or the order of the runtime at this node, and the same at this node. So in other words, d in the recurrence relation here determines not so much the structure of the tree, but the runtime at each interior node of the tree, as we just explained. Now let's conclude this segment by summarizing our analysis. First, we figured out that A determines the width of the recursion tree, and its relationship is proportional. That means if A gets larger, the width gets larger. That is, the total number of nodes per level gets larger. Second, we figured out that B determines the height of the recursion tree. That is, the total number of levels below the root node. Now, this relationship is not proportional. It's inversely proportional, which is why I wrote it as 1 over B. That is, the smaller B gets, the larger the height of the tree, the more levels in the tree. And finally, the constant D determines the amount of work or the runtime at each interior node of the tree. So for example, at the root node, where the input size is n, then the runtime spent at this node is n to the power d, on the order of n to the power d. So in general, we have a constant c times n to the power d. Here n is equal to 64, so that would be the runtime at this root node. Now similarly, at this node, the runtime would be c times the size of the input, power d. Since the size of the input is n over 8, in this case it's 64 over 8, we have a runtime of c times 8 to the power d. And of course the runtime of this node, which is at the same level, is exactly the same, since we have the same input size for every node in one level. So that's the runtime for that node as well. And finally, at the leaf node, we have a runtime equal to a constant, and in this case I'm going to choose for simplicity the same constant c. So what is the runtime then of the algorithm whose execution is represented by this recursion tree? Well, it's a sum of all the runtimes at each one of the nodes in the tree. So in other words, the total runtime is going to be c times, I'm going to factor out the constant c, 64 power d for this level, plus 2 times 8 power d, plus 4 times the constant. So now that we have completed this analysis of the structure of the recursion tree and the impact of the values of A, B, and D on that structure, in the next segment we're going to be able to finally give an intuitive justification for the master theorem.